In this lesson, we're going to discuss water hardness and softening reactions. Water is described as hard when it prevents soap from lathering well, causes scum on bath fixtures, or leaves white, crusty deposits on coffee pots, tea kettles, and hot water heaters. Water hardness is defined as the sum of calcium and magnesium ions, expressed in terms of milligrams per liter as calcium carbonate. So this unit comes into play in hardness as well as alkalinity. Total hardness is equal to the sum of these when they are first converted to milligrams per liter of calcium carbonate. It is also sometimes described in terms of the carbonate hardness plus the non-carbonate hardness, and we'll describe the meaning of that in a minute. So before we get into the water treatment aspect, I want you to understand where hardness comes from and why it is mostly prevalent in groundwater. So groundwater sources are typically plagued with water hardness, or surface waters that are influenced by geology similar to this. So typically you would have rain that trickles into the subsurface and brings with it carbon dioxide from biological processes. The carbon dioxide forms carbonic acid, and that acid causes dissolution of limestone and other clays in the subsurface. And so you have carbonic acid here helping to dissolve calcium carbonate and magnesium carbonate and form dissolved soluble calcium and magnesium rich substances. So when we pump up groundwater or surface waters that have similar reactions occurring, we have a significant calcium and magnesium content. Some rules of thumb of when water is considered hard or soft. Anything over 100 milligrams per liter calcium carbonate will start to generate those deposits and is described as hard. Typically, we would like our water to be around 75 to 100 milligrams per liter calcium carbonate. Anything that's less than that is called soft and has an opposite problem in that it feels very difficult to remove soap when you're washing your hands. Okay, I said that total hardness can also be defined in terms of the carbonate and the non-carbonate hardness. Carbonate hardness is described as the calcium and magnesium content that is associated with the carbonate anion. So when you have a cation, magnesium or calcium, it would be associated with some sort of anion. And when that anion is HCO3 or CO3, then we would say that it is carbonate hardness. Now understand that in solution, these are dissociated, however. So carbonate hardness would equal the total alkalinity or the total hardness, whichever is less. Carbonate hardness is actually fairly easy to remove from water systems, and so it is sometimes referred to as temporary hardness, because heating the water typically removes it. And that's why hot water heaters have a lot of deposits on them. Now, non-carbonate hardness is calcium or magnesium concentration that is associated with other anions. So anything other than HCO3 or CO3. And non-carbonate hardness equals the total hardness minus the total alkalinity. It is sometimes referred to as permanent hardness because it is more challenging to remove from water. The easiest way to visualize this may be to look at a bar chart of total ion concentration on the x-axis. And these are going to be expressed in terms of milligram per liter calcium carbonate. In this part of the bar graph, you have all of the cations, which includes the calcium and magnesium. And on this part, you have all of the anions. The total hardness is simply the sum of the calcium and the magnesium. So you come over and you say that entire section is total hardness, which we'll refer to as TH. But the anion bicarbonate is only paired with a portion of that calcium. And so the carbonate hardness is a subset of the total hardness in this example. The non-carbonate hardness is simply the difference between TH minus CH, total hardness minus carbonate hardness. We're going to work an example now where I give you the milligram per liter concentrations of minerals, and you're asked to determine the total carbonate and non-carbonate hardness in milligrams per liter calcium carbonate. The approach here will be to convert all milligram per liter concentrations to milligram per liter calcium carbonate concentrations, and then to use the equations for total hardness, carbonate hardness, and non-carbonate hardness. I'm going to do my conversions by establishing a table. Calcium is the first concentration that was given as 67.2 milligrams per liter. The equivalent number for calcium is 2. The molecular weight is 40. The equivalent weight of calcium carbonate is 50 milligram per milliequivalent, and the equivalent weight of calcium will be 40 divided by 2 milligram per milliequivalent. This equals 2.5. Recall that the milligram per liter calcium carbonate is equal to the milligram per liter of the species times the equivalent weight over the equivalent weight of calcium carbonate and the equivalent weight of the species. So I come over here and I say 67.2 milligrams per liter times 2.5, and this 2.5 comes from here. That is equal to 168 milligrams per liter calcium carbonate. The second species for conversion is magnesium, and it was given to us as 40.0 milligrams per liter. The equivalent number of magnesium is 2. The molecular weight is 24. The equivalent weight is 50 milligrams per milliequivalent for calcium carbonate divided by 24 divided by 2, the equivalent weight of magnesium. 50 divided by 12 equals 4.12. So to finish the conversion, it's 40 times 4.12, and that equals 164.2. The last conversion we need to do is for bicarbonate. It was given to us in terms of 216.0 milligrams per liter. The equivalent number of bicarbonate is 1. The molecular weight is 61. The equivalent weight is 50 milligram per milliequivalent calcium carbonate divided by 61 divided by 1 for bicarbonate, and that equals 0.82. So 216 times 0.82 equals 177.12. That is the milligrams per liter calcium carbonate. Okay, so the total hardness is equal to magnesium plus calcium in terms of milligram per liter calcium carbonate. That is 164.2 plus 168. That gives 332.8 milligrams per liter calcium carbonate. The carbonate hardness is equal to the alkalinity or the total hardness, whichever is less. And so in this case, alkalinity is 177.12, and that is less than the total hardness. So we will choose the alkalinity as the smaller value, 177.1 milligrams per liter calcium carbonate. And the non-carbonate hardness is equal to the total hardness minus carbonate hardness equals 332.8 minus 177.1 equals 155.7 milligrams per liter calcium carbonate. Okay, so to remove hardness, we do a process called softening. And the softening reactions are based on precipitation reactions for two solubility reactions. You have calcium carbonate and magnesium hydroxide. And we remove hardness when we precipitate out calcium and magnesium. In order to precipitate out calcium carbonate and magnesium hydroxide, you must have carbonate and hydroxide ions present. As you'll recall from the carbonate cycle, carbonate ions are dominant after the pK from bicarbonate to carbonate, And so for these to be highly present in a system, you need a pH of at least 10.3 to get good precipitation of calcium carbonate. And again, this has to do with the transition from bicarbonate to carbonate in the carbonate cycle. For magnesium hydroxide, you need a pH of around 11. At a pH of 11, you would have a molar concentration of 10 to the negative 3, and this shifts the solubility reaction to the right. In the next few slides, I'm going to take you through each of the reactions, but I want to point out here that I highlight why you have to have a high pH in order to get softening to take place. It has to do with shifting that pH to the carbonate ion and shifting the pH to have hydroxide ions. Okay, so the first step is to add lime, and lime is highlighted here in red, calcium hydroxide. Lime is added and it neutralizes any free carbonic acid in the system and precipitates out solid. In the second reaction, lime is also added, and lime that is added, calcium hydroxide, reacts with available alkalinity and hardness. And here you'll see that we added 1 mole of calcium hydroxide and 2 moles of calcium hydroxide here. And in the first reaction, we get out 2 moles of calcium carbonate. So you take one step back by adding calcium as part of calcium hydroxide, but you yield 2 calcium molecules. You throw in 1 mole and you get 2 moles out. With magnesium carbonate removal, you add 2 moles of calcium hydroxide and you get 2 moles of calcium out. So this is sort of a break even on the calcium, but you get 1 mole of magnesium. And so this is the removal in the second reaction. Now, if all available alkalinity has been used to precipitate out calcium and magnesium, then you have removed all of the carbonate hardness. Any addition of chemicals beyond that point targets non-carbonate hardness. Non-carbonate hardness requires the addition of sodium carbonate, which is commonly known as soda ash. It is impossible to precipitate calcium carbonate without carbonate being present. So if all alkalinity is used up, sodium carbonate adds that carbonate and allows for additional precipitation to occur. So when we're targeting non-carbonate hardness, we add sodium carbonate. The carbonate combines with the calcium to precipitate out calcium carbonate, and it produces sodium. Lime would also be added at this point. The hydroxides in the lime would react with magnesium to precipitate magnesium hydroxide, and the calcium that is released from this would react with additional soda ash to precipitate more calcium carbonate. So this is the first reaction of soda ash reacting with calcium. This would be calcium non-carbonate removal. And in these reactions, you have magnesium non-carbonate removal, which actually involves 2 reactions, because in the first, you release calcium, which then has to be combined with more soda ash. Otherwise, you're adding hardness back into the system. So in discussing softening, it's important to understand that excess lime softening has the potential to leave residual amounts of calcium in the water. This is particularly true when non-carbonate magnesium removal is performed with lime. The second point to excessive lime softening is to appreciate that you have to raise the pH to greater than 10.3, and if you're doing magnesium removal, around 11. After you've done the softening and precipitation and sedimentation, it is very critical that you recarbonate the system to bring the pH down. And bubbling in that CO2 recarbonates the water because it adds these back into the soluble form, and it also lowers pH. Let's see where this fits into the treatment train. If we have a softening plant, you have raw water that comes in, you add lime or soda ash if you want to do non-carbonate hardness removal. You go through flocculation, sedimentation, and then you recarbonate by pumping in CO2 gas. You finally filter and you push that softened water into the distribution system.